Hey, thank you all very much, Manuela. It's a real privilege to be part of this seminar. I think it's an extraordinary thing that has been put together, and I've just been amazed to see the great list of speakers. I'm really honored to be part of this. So thank you very much again for the invitation. My topic is on fractional Laplacians, and it certainly is something that's well known to many of you here. And I want to talk about, well, so I called it an unorthodox perspective. I almost called it a quixotic perspective because I think that, I'm taking a somewhat perverse point of view. In some sense, it's just my, you could say my effort to sort of fit a round peg in a square hole or something like that. Or perhaps, just my trying to understand it from my point of view. So maybe take it as that. So this is joint work ultimately with Heiko Gimperlein and Nicoletta Luca. And it's very much work in progress, so I'm not going to be able to give you definitive results, but I'm going to try to tell you sort of a way of thinking about this problem, which perhaps will look fairly unusual. And I want to spend the first, substantial amount of time talking about this setup, which is probably extremely well known to almost everybody, so forgive me for repeating known facts. And I want to repeat sort of the great contributions that have been made in this field before, in particular the work of Gerd Grube, who has really done the seminal work from the microlocal point of view in this area. So I'm interested in the fractional Laplacian. And though I don't think it's strictly necessary, we've been focusing on the case where 0 is less than s is less than 1. But I believe that the results and the methods I talk about will extend more broadly, but this simplifies certain things. And if you forgive me, let me just decrease my pen size there. So let me just remind you a few basic facts. So the basic definition maybe is defined via the Fourier transform, just in a very standard way where I have on Rn. So I'm interested for the moment and almost exclusively in this talk in the fractional Laplacian in Rn, where I send u, I map it to mod c to the 2s u hat of c, and the inverse Fourier transform of that. So this is, I will take as sort of the primary definition. So just to remind you that there are a couple of other competing definitions, and one of them, in fact, will be kind of the key player in my talk. So this is sort of, let's say the most boneheaded definition or the most ancient definition. The second one, well, there's a very famous and early work by Bob Seeley on compact manifolds. And this is maybe in 1968, perhaps. So he defined fractional Laplacians via, one can define them via the functional calculus, if you like, as just from a self-adjoint operators. And then he realized these as pseudo-differential operators of order 2s. So we actually constructed a family, meromorphic family of pseudo-differential operators of order 2s that satisfy the composition laws, Laplacian to the s composed with Laplacian to the t is Laplacian to the s plus t, and so on. And so this has dominated a lot of work in spectral geometry, for example. And then the third method, which I'll be talking about and reminding you of more specifically, is the what I'll call the extension method, which was introduced by Caffarelli and Silvestre. But it is in fact a reflection of sort of a older method in scattering theory, in hyperbolic scattering theory. So again, that was one reason I was interested in this, because it sort of relates to old work I had done on the scattering matrix and on asymptotically hyperbolic spaces. So today, what I'm interested, I'm not doing very well here. Forgive me for a moment. Forgive me, I should have sorry, this is embarrassing. I haven't used this template in a while. I'm just forgetting how to advance pages. I thought I just scrolled down, but that's not what I do. So I think I need to
Yeah, you have just to click on current template.
Excuse me?
Yeah, you there on current template, and it's gonna add it later.
So
squared by y.
Yeah, okay, so, okay, not ideal. Sorry about that. I was using this a lot when I was teaching, but I haven't used it since before the summer. Thank you very much for the guidance. Okay, very good. So now I want to talk about a few of my motivations. So what I'm going to be primarily talking about today is where omega is a smoothly bounded domain in Rn. And the question is, if I look at this problem, Laplacian U is equal to F, we're interested in the boundary regularity theory. And as I had already said, this has been worked out very carefully by group, and there are some partial results by other people. And I'm taking sort of a, trying to, in some sense, recharacterize or look at it from a slightly different point of view. Related to this, I won't sort of say this in too much detail, as setting up elliptic, more general theory of elliptic boundary problems, which she has also undertaken. And let me also sort of phrase this in a slightly more general way of characterization of minimal and maximal domains. Characterization of minimal and maximal domains. And let me sort of say this in a slightly different context, which was one of my motivations for thinking about this problem. So here's a motivation which is very geometrical, looks a bit different, but is very much in the same ballpark. So suppose I have a domain omega in Rn, or it could be just a manifold with boundary, but let's suppose that it has a stratified boundary. So by which I mean that it can be something like a polygon or a curvilinear polygon in R2, or it could be a curvilinear polyhedron in R3, or it could have something more complicated. So I might think about a teardrop-shaped domain, so a solid domain that has a conic singularity on the boundary, or something like this. So it's not going so well. But this, I don't understand why this doesn't just. Okay, there we go. So in general, it's something with some sort of stratified boundary. And so the question that I can pose here is, we know that if it has a stratified boundary, there's sort of non-tangential, non-cusp-like behavior. There exists a Dirichlet de Neumann mapping, or a Dirichlet de Neumann operator. I'll call this N on the boundary of omega. This holds very generally when the boundary is Lipschitz. And so the question is N self-adjoint? Now, there is a sort of a natural self-adjoint extension, which is defined very much in sort of the Friedrichs extension type of way from an extension in the interior. But sort of the more broad question is, what is the minimal and maximal domain, or what are all the possible self-adjoint extensions? Okay, and so this is a bit of an unfamiliar question, but this actually is, there was more there than meets the eye. So for example, if I have a domain that looks like this, it's not very hard to cook up examples where, I can take a function phi on the boundary, I can extend it to a harmonic function. Remember how the Dirichlet de Neumann operator is defined. I can extend it to a harmonic function and then take the normal derivative on the boundary. But there's a surprise. There are functions. So depending on sort of the opening angle or sort of the length of this conic piece here, there are functions which are zero everywhere on the boundary, but blow up at that conic tip, and which have non-zero normal derivative. So, all of these sort of entered the discussion. And if you have sort of edges and, corners, then you have a lot of these things sort of interacting. And the question is, how do you sort of codify all of these? And, the answer is that there can be many different possible self-adjoint extensions. And again, this sort of relates to understanding what is the minimal domain, possible domains of self-adjointness, and the maximal domain. So this is a question I'm very much interested in understanding for various reasons. And this is sort of joint ongoing work with Pierre Albin and Jeremy Marzuola. So I just wanted to mention that because, in fact, it's very much in the same package of ideas. And okay, so let me now move back to, and remember, the connection is, of course, that the Dirichlet de Neumann operator is very much close to, very much related to the square root of the Laplacian. So of course, it's not exactly that, except for in very special cases, but it's that plus a smoothing operator, or that plus lower order terms. Okay, so now let me remind you about the extension method. So the key there is you think about Rn. So let's leave out the domain for the moment. I think of Rn as sitting in as the boundary of the upper half space. I'll let the variable be t. I define a degenerate operator, L sub s, or singular operator, as d by dt squared plus 1 minus 2s over t d by dt plus Laplacian sub x. I'm going to think of the variable here as capital X. Okay. Now, if I have a solution of L sub s of capital U is equal to 0, so there's a very general theory of operators with this type of degeneracy. Many people have developed various versions. I have some version, but again, this goes back many years to many different authors. Any such solution is going to have an asymptotic expansion in terms of what are called the indicial roots of this operator. So the indicial roots of this operator are 0 and 2s, which means that there's formal solutions of the form t to the 0 and t to the 2s. If I insert either of these things into the equation, they get killed. So it turns out that any solution is going to have an expansion that looks like t to the 0, u1, t to the first power, plus dot, dot, dot. And then I'm going to have a v0, t to the 2s, plus v1, t to the 2s minus plus 1, plus and so on. Okay, so this is a general regularity theory. In general, the ui's and the vj's are just distributions on Rn. And it's very easy to create solutions where, in fact, u0 is some distribution, and then u1 is one order less, u2 is one order less. So this is what's known as a weak type expansion. It only makes sense as a classical expansion if you integrate by, if you pair with the test function in the x variable. But in any sense, you can make sense of it. And the free variables, I mean, this formally solves the series. I mean, if I plug u into this equation, terms match up and get killed. And the free variables are u0 and v0. So formally, you're allowed to plug in any u0 and v0 that you wish. But if you have an actual global solution on the half space, then these things are functionally related to each other. And in fact, v0 is a functionally related to u0, and it's exactly Laplacian to the s of u0. Okay, now why that comes about is because if I look at the solution, so if I suppose I take Ls of u is equal to 0, okay, and I take the Fourier transform in just the x variable, the only free variable where I have a full thing. So then this operator becomes, so Ls hat, I might call it, becomes dt squared plus 1 minus 2s over t dt, and then minus mod c squared. Okay, so if I look at Ls hat of u hat is equal to 0, I get, this is a Bessel equation, and I can write down the solution that u hat is going to be some function. Well, it's going to be, let's say a0 hat of c times t to the 2s, t to the s, forgive me, mod c to the s times k sub s of t mod c. And then there's another possible solution, b0 hat of c, t to the s mod c to the s, I0 s, I sub s of t mod c. Because we're using Fourier transform methods, we have to kill the exponentially increasing guy. So these are Bessel functions of imaginary order. We're only allowed to sort of stick with this guy. And if I look at the asymptotic expansion of this term, I get exactly what I had on the previous page. Okay, so namely, u hat is going to look like this sort of a0 hat t to the 0 plus dot, dot, dot. And then there's going to be some multiplier of it, which is going to be, in fact, exactly mod c to the 2s times a0 hat of c times t to the 2s plus higher order terms. So this is exactly relating to the Fourier transform definition. And I'm forgetting some functions of s there and so on, some extra coefficients. But that's where the fractional Laplacian, from the Fourier transform point of view, relates to this extension method. Okay, so again, forgive me if that's utter review, but I felt impelled to say these things. Okay, so what's the next step? So what's the problem that we're interested in? So the problems are, well, I'm looking at Laplacian sub s of u is equal to f in some domain omega. Okay, so I'm interested in the following things. So suppose I let u0 be u in omega and 0 in omega complement. And really the right way to say this is I want to think of u as a distribution in Rn, which is supported in omega. So, or if you like, it's something that's extendable by 0. Seem to be alternating check patterns on the pages here, just to keep things livened up. Yeah? Okay, so I take this function, u0, I map it to the solution, capital U. So this is this, remember, this is a solution of LS of capital U is equal to 0, and U restricted to t equals 0 is equal to U naught. And then I map this to its Neumann data. So, and I call its Neumann data this sort of the t to the s, the t to the 2s coefficient. And this is going to look like the limit as t goes to 0, t to the 1 minus 2s dt of capital U, and that's going to be exactly the function f. So that's the definition of the fractional Laplacian. Now, what's interesting about this is that if now I'm going to sort of typically think about the model case, and one of the points of microlocal methods or geometric microlocal methods is if you understand the model case well enough, then all the sort of curving, putting it in sort of more general, smoothly bounded domains is just there's some glorified machinery to do perturbation analysis, right? So the whole key is to understand the model case. And in my case, the model case is going to be where the Rn plus is the set where x is, I'm going to let capital X be little xy, x is greater than, x is in R, y is in Rn minus 1, and Rn plus is the set where little x is greater than or equal to 0. So I'll take this as my model domain, obviously. And so the new feature is that I have this interface, and I'm looking at functions which are 0 on the left-hand side where x is negative. Okay, so so the question is, what can I say? I mean, so the basic questions are if U or F, let's say, if let's say F is in some well-known space, so for example, C0 alpha of omega bar, or some Sobolev space, so I won't list all the possible spaces, then what is the regularity of U at x equals 0? Okay, so that's the basic question I'm asking. And obviously, is it solvable? Well, by the Fourier transform technique, we know that there is some solution. So really, it's just a question of what does it look like. Okay, so there's a rich history here, and just to remind you of a few high points of this. So there was a famous paper by Rosaton and Sarah in 2014, where they gave some sort of partial answer. So I'm going to let, so if I have F, which is in L infinity, so I believe that this was the result, F in L infinity, then that's going to say that U is lies in some small, and I believe some small x to the, so this is x to the s times C0 epsilon of omega bar for some epsilon greater than 0. Okay, so they established some Holder regularity at the boundary. And again, of course, you're assuming a very weak right-hand side. So, so there is an older technique that goes back to Hermander in '66, and this is exactly what Grube expanded considerably. But one of the consequences of Hermander's work was that if F was in C infinity of omega bar, then U was in, I'll write this as x to the s times C infinity of omega bar. Okay. So this is, of course, in some sense imposing some sort of Dirichlet boundary condition. So you're assuming that, we're assuming that the function kind of vanishes or has some sort of leading order term that vanishes at the boundary. Okay. So, okay, so the actual, the full theory is that Grube developed was defined in terms of some function spaces that are somewhat complicated to state. And in some sense, it's trying to understand these function spaces from sort of a non-microlocal point of view, or sort of a different microlocal point of view that got me interested in this problem. So let me state some definitions of spaces. So, so I'll just maybe do this only in the Holder regime, but there's Sobolev analogs of these. So I'm going to take C star mu of sigma. So C star is sort of the usual Zygmunt type Holder extensions of the Holder theory. So they agree with the ordinary Holder spaces when S is positive and non-integral. So I'm going to define these spaces with sort of a mu of sigma, sort of two indices up top of omega bar. Okay, and so this is my definition. So I'm going to write this in terms of an operator, lambda plus to the minus mu. So this is a regularity changing operator, lambda plus to the minus mu extension operator. So E plus is what extends something by 0 outside times C bar star of sigma minus mu. So I believe this is the right definition. And this is valid, for example, when sigma is greater than mu minus 1. Okay, so this space here is the ordinary Zygmunt Holder space. This E plus, it says you take this Holder function on omega and you extend it by 0 outside. And then you apply this operator, lambda plus to the minus mu. So lambda plus to the minus mu. So it's roughly equal to, so let me put this, it's not exactly that because you have to modify the definition. It's the pseudo-differential operator. Well, once you modify it properly, it's the pseudo-differential operator of order C prime plus, let's get the right thing here. So it is the pseudo-differential operator associated to the symbol. So sorry, I'm just trying to make sure I say the right thing here. I'll make some grievous error. So well, let me sort of write, let me write this in the following form. C primed plus I mu plus I Cn to the minus mu. Okay, so now this doesn't quite work because this guy is not quite a good symbol. It doesn't satisfy all the symbolic estimates. So this approximately equal means that you have to actually sort of put a special type of cutoff function in here so it works. And that was sort of a very clever innovation that Grub put into this business. Okay, so the point being that, you have a function that's a Holder up to this boundary, you extend it by 0, and then you apply this, somewhat mysterious regularity changing operator, lambda plus to mu, and you get these function spaces, which I called C star mu of sigma. Okay, so let me, and so she has a very thorough characterization of what these things look like. So C star mu of sigma is actually equal to things which are supported, C dot star sigma of omega bar in the low regularity regime when -1 is less than sigma minus mu is less than 0. But they actually are only contained in, so what I'll call C dot sigma star of omega bar plus D, so let me write this as D mu E plus C bar sigma minus mu star. And these are in turn sort of contained in just D to the mu, excuse me, by D to the mu, I mean, think of D as being X. So forgive me, D is in her notation is distance to the boundary. So forgive me, distance to the boundary E plus C bar sigma minus mu star. Okay, so this is some subclass of the space of things which vanish to order mu at the boundary, and there are Holder functions which are Holder of order sigma minus mu up to the boundary extended by 0 and then squashed down by the distance factor D to the mu. Okay, so it's a nice space. Of course, here you have exact equality, which is good. Here, I mean, you have a clear-cut definition of what the space is, but you only know that it's contained in this sort of more familiar space, and you don't know the exact equality. So this just says that it's a little bit hard to get your hands on completely, or at least to think of in terms of very concrete terms. And but again, that may be partly my failing, and what I'm trying to do is reinterpret this inclusion or trying to characterize this space in a slightly different way. Okay, so her main theorem, which was this terrific achievement, was to say that, so now she worked in the framework not via the extension operator, but thinking of, so you regard Laplacian to the S as a pseudo-differential operator P, order 2S, which satisfies a certain variant of the so-called transmission condition. So satisfying a variant of the transmission condition. And just to say in words, I won't write it down, but it was recognized a long time ago in microlocal analysis that boundaries and pseudo-differential operators don't mix very easily if you don't do anything clever. So namely, if I take a domain with boundary and I take functions which are smooth up to the boundary and I hit them with a pseudo-differential operator, the result need not be smooth up to the boundary anymore. So it just, just a failure of the general definition of pseudo-differential operators, or, that's just how nature works. You can take your pick. But there are specific conditions you can put on the symbol, the full symbol of the pseudo-differential operator at the boundary, which do guarantee that smoothness is preserved. This is called the transmission condition. It was discovered by Boutet de Monvel, and it played a very significant role in many developments since, including Grubb's theory of boundary problems. And so there's a modified version of this transmission condition. I'm not going to write it down technically here, but so here is the theorem she proved that if sigma is greater than S minus 1, I hope I have my indices right, and if F is in C bar excuse me, I want to say C bar sigma star, and Laplacian sub S of U is equal to F. So I look at the regularity of the solution. So I have a complete characterization. U is in C sigma, excuse me, S times sigma plus 2S. S times sigma plus 2S. So this is not times, this is sigma S comma, S parentheses sigma plus 2S, right? I've used these function spaces on the other side. And this comes with the proviso that sigma plus S and sigma plus 2S are not in the natural numbers. So it's a complete solution to this problem, but it's phrased in terms of these spaces defined via Fourier transform, so they may be hard to get your hands on, for example, numerically, if you want to do numerical approximations or things like this. Okay, so I say all this, and this is sort of a lengthy preamble, but just to sort of give you sort of a sense that there are very complete results in the background here. And so I'm not, in some sense, new. Okay, so here comes the quixotic part that I talked about. So this is, again, I remind you, work with Heiko Gimperlein and Nicoletta Luca and myself. And it's very much work in progress in the sense that we have a long way to go to get sort of definitive results, but we have a pretty good strategy and fairly good partial results as we go along. And so let me remind you again of this model situation. Here's Rn minus 1 sitting inside R of n, and all of this is sitting inside the upper half space, Rn plus 1 plus. And so the point of view, so this is a very geometric point of view, is I should think of this as what's called a stratified space. So this is a, and let me sort of write it in parentheses, a depth 2 stratified space. It's a very particular type of one, but that perspective is useful. Now, what is a stratified space? It's something that may not be exactly a manifold. In this case, it's only mildly worse than a manifold. It's a manifolded boundary, but with sort of this sort of distinguished or marked subspace in the boundary. Now, in general, what a stratified space is some topological space that's sort of put together from smooth manifolds of various dimensions. I won't give you the various technical definitions, but you can think of domains with conical points or edges or something where there'd be a big, huge smooth stratum. And then I sort of add on various boundary layers that are submanifolds of different dimensions. Okay, so polyhedra have examples where you have edges and vertices and of higher, intermediate dimension when you're in higher dimensions. And there's an emerging and, now rather sophisticated theory of analysis on stratified spaces. And so why do I call this a stratified space? Because I want to single out that there's behavior in the interior, which is where the solution capital U lives. There's behavior at the boundary where the boundary values live. And then there's sort of this lower dimensional interface where things are changing. So somehow you want to sort of bring out that geometry to some sort of picture. Okay, so the technique that we use is one that I've been using for many years in various other contexts, which is I want to blow up this the interface at t equals 0. So I'm going to draw a picture, which looks a bit funny, but so I take this up, and the process of real blow up is what I'm doing is I'm replacing every point here by its spherical normal bundle. Now this is a codimension 2 submanifold, so I can just reduce really to the upper half space here. This is 2 dimensions, R2 plus, and by blowing up, or what is the spherical normal bundle of a point? Well, I'm just introducing polar coordinates. R cosine theta is equal to x and R sine theta is equal to t. And I sort of take these seriously, which means that I'm really looking at the space where R is greater than or equal to 0. Theta is in 0 pi, forgive me. So that's this theta angle. But in particular, I'm adding in the face at R equals 0. So what I've done is I've replaced the origin by this semicircle. Okay, so just kind of a stupid trick. I've just introduced a singular coordinate change, but I want to say I have a new space. This is a manifold with corners. And the philosophy of things is that once I've done this singular coordinate change, things are going to be smoother. Okay, it sounds a bit weird, but I can say this in words that I have a degenerate or a singular operator like L sub s, and things look bad. And this degenerate operator with this interface at little x equals 0. And in order to understand or resolve that situation, I perform this singular coordinate change, take those coordinates sort of seriously in a geometric sense, namely I define a new space in which those are smooth coordinates. And then sort of the miracle occurs is that everything looks much smoother on this blown up space. okay? And well, I won't give you the long history of this, but let's just say it works in many, many cases. Of course, it doesn't work in every case, but this is sort of a very general philosophy that has produced a lot of interesting mathematics. So if I do this at every point of this sort of interface here, what I get is a space that looks kind of funny. You can sort of think of it as sort of a little half of a garden hose or a half of a tube all along that y = 0 axis. So it's this picture crossed with Rn - 1. Okay, so this is sort of the space in which we should be doing analysis rather than here. So, before, here was x greater than 0, x less than 0, and then t. And the claim is that here, sort of the upper half space, but bounded by something that now has two boundary hypersurfaces and then these corners, is where everything is going to look smoother. And that's really kind of the punchline of my story. Okay, so let me go back to this picture for a moment. And I want to point out a feature which it's not completely obvious, but so here is sort of the theta direction, right? This is theta. And here is the r directions. And I can really think of this thing as this is a cone over the interval. So I can write this as a cone over the interval. Sorry, the letter C is overworked here. It's not Holder spaces, but a cone. And so, I mean, ordinarily I would think of the cone over an interval as well. I can figure it various ways. I could also picture it as kind of like a cylinder. So here's, theta going from 0 to pi and r greater than or equal to 0. But I can sort of just curve it around or stretch it around like this. Now, why do I call this a depth 2 space? Well, because there's, Rn - 1 sitting in Rn, sitting in Rn + 1 half space. Or another way to think about it is I can think of this thing as a cone, but the link of the cone, the cross section of the cone itself has a singularity, which in this case is just a boundary. So if I were to take a cone over a circle, then there's sort of a very well-known theory of conic spaces. And this is, you can sort of think of as just a generalization of looking at Laplacians or, Laplace type operators on spaces with conic singularities. The difference here is that the cross section of the cone has a boundary. Okay, so, a natural generalization is, take a disk or some other manifolded boundary, and I have a cone over a manifolded boundary. I get something with, a regular smooth boundary, and then I have sort of this worse vertex at the bottom. And if you remember way back to the beginning of my talk, I talked about Dirichlet-de-Neumann operators and domains with singular boundaries. This is exactly the kind of picture you might have in mind, that you have a domain where you have the Laplacian, you have its Dirichlet-de-Neumann operator out here, and then the addition of this extra vertex at infinity, or at the boundary of this thing, causes sort of new phenomena to happen. Okay, so enough of these sort of geometric workup. So you can do this sort of more generally. If I have a domain omega, which is something compact and smoothly bounded, I can sort of blow up this thing. And I won't draw the picture, but basically I'm sort of taking these semicircles at every point here, and I get a new space which has three boundary components. Sort of I have the interior boundary component, which is omega, the exterior, and then this sort of new tube, and my picture kind of makes it look pretty mangled, but the tube where I have sort of these semicircles, this bundle of semicircles. Okay, so let me tell you the basic fact here. So here's a basic fact, or let's just say a theorem, as theorems are supposed to be facts, right? So if f is in C infinity of omega bar, right? And then I do the same trick of solving Laplacian to the S of u by extending f to be 0 outside, solving via the extension method, and then looking at the corresponding solution u. So I have L sub S of u is equal to 0. Then the theorem is that u is polyhomogeneous on the space, let me call it capital X. So here's my space capital X. So capital X is the space blown up at the interface in this funny way I've done before. What does polyhomogeneous mean? Well, morally it just means smooth, right? So what it really means is, so polyhomogeneous, sometimes this is introduced as written as PHG. This is an old condition that is sort of the right replacement for smoothness on manifolds of boundary or corners. And it just means that this function u has expansions, has classical asymptotic expansions at every boundary component. At all boundaries and corners. And let me just say explicitly, product type expansions at the corners. Okay, so you know, what I'm really saying is that if I start off with smooth data, this is actually kind of a reinterpretation of Hermander's result. So here is this thing, and so I have the solution capital U up here. It's going to be smooth down to here. It's going to be smooth down to here. It's actually 0 there, so I'll put a 0, by which I mean the function is vanishing at that boundary. And here it's vanishing like r to the s. Okay, and it's better than just vanishing like r to the s as I look at, so if I think of u in these sort of funny coordinates, u of r theta y, it actually has an asymptotic expansion as r goes to 0, but let's say theta is in the interior. So as I'm going here, right, that this has a classical expansion that looks like r to the s plus j times uj of theta and y. Okay, so again, this is sort of a really simple statement because I started with smooth data. So, you know, of course, there are infinitely many conditions, but it tells you that what you have is something that, you know, it's sort of the type of solution that you always love in PDE, that you start off with something smooth and the solution is smooth. Now, polyhomogeneity is the right notion of smoothness, and of course, this is not smooth because I have this sort of fractional exponent in here, but it's saying that, you know, this has this extremely nice behavior as I go towards this face that's undetected if I do this blow up, or it's at least harder to understand that behavior. So in other words, and this is again kind of the whole circle of ideas in a single thing, if I look at sort of the interface like this, and I'm just staying in Rn, I have some sort of funny regularity happening at this point, which is hard to understand. If I pass the blow up in the upper half space and look at it in spherical, in these polar coordinates, it becomes a very sensible type of behavior. Okay. Okay. So so then the question, and then the sort of more serious question is, okay, so what if f is only in C0 alpha? Okay, what can I say then? So, you know, again, you know, what we're interested in is I look at this face here. And I have a function which is f over here, 0 over here. I find the corresponding solution u. And what I'm asking is, and L sub s of u is equal to 0. And what I'm asking is, what does u look like? Well, over here, you know, the boundary value of u. So, you know, what I know is that u at t equals 0 for x negative is 0. Okay, over here, I know that t to the 1 minus 2s dt of capital U at t equals 0, x positive, converges to little f of x, little f of x and y. Okay, so what do I know about capital U over here? It's smooth. So it's actually, so capital U is smooth, C infinity, up to t equals 0 when x is negative. That's just local classical, well, local elliptic regularity theory for this degenerate type of operator. Okay. What does it look like over here? Well, it's, you know, the boundary value, if I sort of stay away from the boundary, it's just Holder, you know, it's Neumann data as Holder up to the boundary. So it's going to look, so when x is positive, right, u is, u at t equals 0, equals little u. Well, you know, this is a pseudo-differential operator of order 2s. So this thing has to be in, well, let me just write it briefly as C alpha plus 2s. So it's going to be order 2s order, it's more regular. Okay, so that's just sort of classical elliptic theory. So the real question is what happens near this front face, which is sort of the expansion of the interface. Okay, and on the front face, so I'm thinking of u now as a function of r and theta and y. So remember, r is sort of this direction and theta is this direction. Okay. So I'm interested in what does it look like? And I've already indicated that u should look like r to the s times u naught plus higher order terms. But how regular is this u naught, right? If the boundary value is only C0 alpha. And the answer is it's regular in one direction, but not very regular in the other direction. So this u naught is a function of theta and y. And, you know, interestingly, it's very smooth in theta. So in these sort of semicircle, so let me sort of draw this picture again. In these sort of semicircle variables, so if I fix y and go across in theta, it's actually quite smooth. So let me tell you how smooth it is. So in theta, there's an operator, which I'm going to call q sub theta, which is d by d theta squared, plus let me see, there's a 2 minus 2s times cotangent, no, excuse me, it's 1 minus 2s, forgive me. Well, sorry, I forgot the coefficient there. Cotangent of theta d theta. So there's an ODE in this variable. And what I know is that q sub theta of u naught is equal to 0, of theta and y is equal to 0 for each y. Okay, so in other words, it says that as I sort of look at the function just on these semicircles where I hold y fixed, it's a solution of a very simple ODE. I can say everything about the ODE. I know sort of the solutions of it. They're actually derived in terms of generalized Legendre functions. And so you have a completely smooth behavior. So, you know, what's left is to analyze sort of the behavior in this transverse direction. So, you know, the statement is that in this direction, it's smooth. And in this direction, it's in some sense, well, it lies in some sort of Holder space. And I think in the interests of preserving everybody's sanity, at least at my 8:15 in the morning, I'm not going to write down the condition very technically, but well, let me sort of say what it is, but maybe not go into too great detail because I want to say a few other things before the talk is finished. But sort of there are interesting vector fields that one needs to sort of phrase everything by. And let me sort of write down what the vector fields that I'm interested in are. So I'm going to have the vector fields r times theta dr, r times theta dy, and then theta d theta. And really, I should be replacing these thetas by sine of theta. So these are vector fields on this funny manifold with corners. I just want to point out some features about them. So these are vector fields. So maybe I should say a little bit more clearly: r times sine of theta d by dr, r times sine of theta d by dy, and then sine of theta d by d theta. So these are the things I really mean. These vanish. They vanish here and here, because every single one of these vector fields has a sine of theta here. And you know, the easiest spaces on which to prove regularity are to say, my function is going to be infinitely differentiable with respect to these vector fields, right? And this is actually kind of a funny statement, but it says that I take these degenerate vector fields and I can apply them to the solution U, no matter what the boundary data looks like. I can apply these vector fields arbitrarily many times, and doesn't get worse. Okay, so that's really saying that when r and theta are positive, when you're in the interior of the space, the function is smooth. That's no great shock, right? But it's telling you exactly how it degenerates at the boundary. Okay, so this is so these vector fields have sort of double vanishing. So they vanish. Some of them vanish at r equals 0. These guys, and this guy does not vanish at r equals 0. So let me sort of state this again, because the statement I made in the last sentence here. So let me sort of redraw this picture for the umpteenth time. Okay, so remember I have r sine theta dr, r sine theta dy, and sine theta d theta. So the fact is that I have this solution U has the property, and this is regardless of sort of what its boundary data is, what, you know, the regularity of F. So U is of stable regularity with respect to these vector fields. So for example, I could say that, you know, U lies in some space. Let's say, just to be very simplistic, it lies in L infinity. And I apply these vector fields any number of times to the I, R, sine theta dy, to the J, sine theta d theta, d theta, to the K of capital U. It still lies in L infinity for all I, J, and K. Okay, so that's a very strong regularity statement. And it's telling you exactly how the regularity of U can degenerate as I get to the boundary. Now, this is much weaker than what I told you before, that I'm holder up to this face and I'm smooth up to that face. So in fact, there has to be some improvement using the actual boundary data, the fact that I'm vanishing over here and that I have holder initial data here to improve the statement. So this is kind of, in fact, just a scale invariant regularity statement. But the thing I wanted to point out is that at r equals 0, the fact that I'm of stable regularity tells me this vector field is non-vanishing. It says I can apply this arbitrarily many times. It says I'm smooth in theta, right? So the fact that I'm smooth in theta comes from the very simplest regularity statement. But the smoothness in y is saying that basically r dy of U to the L stays the same. Okay, so this is kind of a funny statement. It's just saying that the y derivatives are starting to oscillate at some rate. Like, in fact, they're going to oscillate at rate sort of essentially r to the alpha minus 1. So in fact, these look like r to the alpha minus 1 as r goes to 0. Okay. So, you know, as I say, this is a fairly geometric way of understanding regularity, but this is sort of a sharp statement in a different kind of way than the microlocal statement is. Okay, so it gives you a good way, and it actually seems to be, my collaborators assure me, sort of a way that may be more tractable for numerical computations. Now, I'm going to stop in just a moment, but I just want to say a few words about the techniques of how these things are proved. So a few words about techniques. And again, sorry for not writing sort of a very specific theorem that takes a while to introduce the language, and I wanted to give you a few of the geometric ideas rather than focus on the setting up a lot of function space definitions and things like this, though one can certainly do it. So the technique is really what we'd like to do is I take this space and I'd like to understand the precise structure of the Poisson operator, and I'm going to call this the mixed Poisson operator. So this is the mixed Poisson operator. What do I mean by that? Well, so P sub m of f is going to be the function u, where f is supported over here, it's 0 over here. And when I say mixed, I'm sort of looking at things which have Dirichlet boundary value 0 over here, and the sort of generalized Neumann data f over here. So that's what I mean mixed. I mean, I just have different boundary conditions on the two sides of this interface. Okay, so really what I'm interested in is what is the structure of P sub m? Okay, because ideally, if I know what the operator P sub m is, then I should be able to read off regularity properties. What do I mean? What do I know about the operator P sub m? Well, let me give you two examples. Let me take the Dirichlet Poisson operator. So this is the operator that I feed in u, and I get capital U. So namely, I feed in what the Dirichlet data is on either side, and I get that. Now, what's nice about this is I can write down this thing just explicitly. So in fact, there's a nice specific formula for P sub d, and I'll give it to you right now. So P sub d is going to be a function of t, little x tilde, little y, and little y tilde. Okay, and here it is. It's going to be some constant times t to the minus n, and then I'm going to have x minus x tilde squared over t squared plus y minus y tilde squared over t squared plus 1. And this is all raised to the power minus n plus 2s over 2. Okay. Okay, so there it is. I just want to point out that this is something that if I were to sort of do this artifice of writing things in polar coordinates, so in polar coordinates, this is actually very simple. So let me choose polar coordinates where I take t, x tilde, and then y minus y tilde. This thing is obviously translation invariant in y. Now, this thing looks translation invariant in x2, but remember, I'm going to introduce an asymmetry by cutting off at x equals 0, little x equals 0. So I'm going to set this equal to rho times omega, where omega lives in a hemisphere. So it's whatever the dimension is. So this is n minus 1, n plus 1, so n plus 1 plus. So this omega lives in a hemisphere. And so, you know, that means that rho is equal, you know, so t is equal to rho omega naught, x is equal to rho omega 1, x tilde is equal to rho omega 2, and y minus y tilde is equal to rho times all the other variables, omega primed. If I write this P sub d as a function of these things, what am I going to get? Well, everything inside here is homogeneous in rho. So I'm going to get a rho to the minus n, omega naught to the minus n, and then I'm going to have omega 1 minus omega 2 squared over omega naught squared plus omega primed squared over omega naught squared plus 1 to the power minus n over 2 minus s. Okay, and of course I can pull out the omega naught squared, so this is going to be rho to the minus n. I'm going to have omega naught, so this is going to be omega naught to the s, I guess, times omega 1 minus omega 2 squared plus omega prime squared plus omega naught squared to the minus n over 2 minus s. Okay, I wrote this down explicitly just to convince you that if you write in polar coordinates, then it actually looks very simple. I mean, this didn't look too bad either, of course, but it, you know, it looks actually quite simple. You know, so namely, it looks like just powers that blow up or decay at certain very specific rates times smooth functions. Okay. So the moral is that, you know, for the, so now what's nice about this Poisson-Dirichlet kernel is that, Dirichlet-Poisson kernel is that there it is, it's explicit, and I've just restricted to things for x greater or equal to 0. I can understand exactly how it lifts to this sort of funny blown up space. So the core of our work is that the mixed Poisson kernel, Poisson mixed, so on this side, it looks like P sub D. On this side, it looks like the Neumann-Poisson kernel, both of which I know explicitly. There's an equally explicit formula over here. And then somehow over here in this sectorial region, it has to sort of make a transition from the Dirichlet to the Poisson kernel, to the Neumann-Poisson kernel. So the hard work is actually constructing this P sub M, okay? And so this P sub M is again, it's a function of all of these variables, x tilde, y minus y tilde. And it's, so, I mean, here's kind of finally the real punchline, and then I'll stop, is that this thing is well, smooth, by which I mean polyhomogeneous, on some blowup of where you'd expect it to live. Well, so this is R plus T cross R plus x tilde. I want to let the whole R space here cross Rn minus 1 in the y minus y tilde variable. So namely, I've cut off the x tilde variable to be positive simply because I'm demanding to only feed in data which is 0 on one side. But then I want to understand what the output looks like on the other side. Okay. And so I could draw a funny picture, maybe I'm tempted to do so just as sort of a final poke in the eye, that here's what the picture looks like. And it's a really bizarre picture. And I'll try to explain it and then I'll be done. So what I've done here is drawn a bad picture, but what this picture is supposed to represent is I've introduced polar coordinates in this space. So here's the t coordinate, here's the x tilde coordinate, here's x and y minus y tilde. I've blown up the origin in this space. That's this funny bubble here. Okay, I've blown up the diagonal. So the diagonal where x equals x tilde and y equals y tilde at t equals 0, I've blown up here. And then I've also blown up the interface where x equals 0. So I've done this sort of, you know, if you like, I've just introduced 3 separate singular coordinate systems iteratively. Okay, I get this bizarre looking space, and the theorem is that this P sub M is smooth on this space. Okay, so what good does a statement like that do you? Well, it says that if I apply P sub M, I can sort of just read off looking at the various orders of vanishing on these various faces and commuting vector fields through, I can read off mapping properties of P sub M very accurately. Okay, so that's the idea, and I'm going to stop there, but just to say that this is, you know, part of a whole sort of general strategy is applied in a lot of other problems. We don't know the end of the story here, and what I'm hoping that this will eventually do is give sort of a what did they say in the relativity community, a physical space as opposed to Fourier transform space interpretation of Grub's function spaces. So I expect, I mean, you know, in some sense, they have to be the same answer. She had a sharp characterization. We're going to have a sharp characterization. They have to be the same thing, but they're not apparently so. And one of the mysteries we haven't unlocked is why they're the same, except for abstractly. So let me stop there.